Hello, I'm Ashutosh Bapat, major contributor to PostgreSQL. I'm part of PostgreSQL contributors team at Microsoft. Today, I will talk about logical replication, which is a relatively new PostgreSQL feature, and it receives a lot of improvements in every release. So let's get started. Okay, let's talk about logical replication. Logical replication in PostgreSQL um, inherited some of the structure from physical replication. So we'll talk about physical replication first, and then talk about logical replication, its components, what val sender does, what logical receiver does, what role replication slots play, and what to watch for. And then we'll conclude this presentation. Um, Physical replication is an old feature in PostgreSQL. It is meant to replicate the physical view of the database. That is what is on the disk. So here in the picture, we see that there is an origin or upstream, which is a normal PostgreSQL server where there are backends running, clients connecting, and they are making changes to the database. On the left bottom, you will see the disk view, and the backends make changes to that disk view or the physical view of the database. While that change is made, each change is recorded as what is called as write ahead log. This write ahead log basically tells which bytes at what offset in what page and in which file have been changed. This wall record is written first, and then the physical view is changed. In order to replicate the data, what needs to be done is we take snapshot of the disk at a given point of time along with the wall and copy it over to the target or replica. Now this physical view is exactly same at that point along with the wall. We start applying those walls, and when we have exhausted the copied over walls, we start streaming the walls as they are generated and apply to the physical view, thus bringing the physical view on the target at the same level as the origin, and thus maintaining the replica or the consistency between these two views. Now, eventually, the physical view on the target will be same as the origin, and since the physical view is same, the logical view of the database, that is what the results the query is written, will also be same automatically. And now that's how you have a replica set up with the physical streaming, usually for standby. Now, what happens here is since we want to maintain the physical view in sync on the between the target and the origin, we cannot modify the physical view on the target. If we modify, then that will lead to the corruption or the logical view being inconsistent between these two systems. And so the target is really only a read-only replica, and it cannot be modified. It cannot be active. With logical replication, we add more intelligence to this system. As you will notice that there is still origin, there is still target, but um, the disk view on origin and target, which you can see as the disk symbols at the bottom, is different. And the reason it is different is because we do not send the physical view of the database and also the physical wall. Instead, some intelligence is built at the origin to read the wall and convert it into a logical change. So instead of that change saying these bytes at this offset on this page in this file have changed, it says that this table, this row, this column has changed, or in this table we have inserted this row, or we have deleted this row from this table. So the physical change is now converted to logical change and sent downstream to the target, where on the logical receiver on the target receives this change and applies it on the physical view of the target, producing different series of wall at the target system. In a way, this logical receiver is like another backend, another PostgreSQL backend, making changes to the database and generating wall. As you will notice that now the target is almost acting like the primary or the origin, in the sense that it is active. It can accept connections, it can have its own backends, it can have its own tables, which may be separate from the origin, or there may be some common tables. But the crux is that the target system is as active as the origin system. And this is the first benefit of logical replication, that both the systems are active. We don't need to wait for promotion for the target to come up in case origin goes down. Let's dive deeper into um, the, the mechanism of the logical replication. Let's talk about the upstream first and the wall sender there. So on the upstream, we still read the wall, but instead of just sending it down, we convert it into a logical change. It, we should also notice that the logical view of the database consists of only the committed transactions. Any transaction which has made changes to the disk but has aborted does not contribute anything to the logical view of that database. We take advantage of this fact, and the upstream only sends the committed transactions to the target. With streaming logical replication, that changes slightly a bit, the underlying mechanism, but um, the principle remains same, that only committed changes appear on the replica. The second change that we will notice is when we are interpreting the physical change, we have to interpret it in the context of the transaction. And so we have to know under what transaction a particular physical change was made, so that that physical change can be converted into a logical change using the view of the database at the time of recording that change. For, for this to work, we reserve an area in memory called reorder buffer, where we segregate the walls by transaction. As we can see that there are three transactions here: orange, blue, and yellow. And in the reorder buffer, their walls are segregated. If this memory area fills up, one or more transactions are chosen as victim, and their changes are flushed to disk to make way for newer transactions. When a transaction gets committed, if it's already there in the reorder buffer, it is passed to logical decoder. If it's on the disk, it is pulled from the disk and passed to logical decoder. Now, logical decoder is the one which converts this physical record into logical record and sends it downstream using the snapshot at that point in time. When on the target system, the logical receiver receives these logical changes, it has to know where to apply these logical changes. The tables on upstream and downstream may have the same name, but they have different physical locations and OIDs than the upstream. And so the logical interpreter has to know where on the physical view of the target should this change be applied. And then it applies that change. And while it does that, it maintains transaction state so that the change that is being made does not become visible. Um, Again, this acts as this acts very similar to any other client backend, and other backends can continue to run while the logical receiver is working. So, in order to, whether it's physical replication or logical replication, the upstream has to know how far we are in the wall stream in order to replicate it. How far a particular target has received wall from the upstream. The wall which has been already received and acknowledged can be released, making the disk free. But for doing that, it has to know the progress of this replication. And that is done through replication slot, which maintains this progress. And when it maintains this progress, it also holds back the resources like wall, as we saw. Those are the ones that are interpreted and sent downstream. Then catalog tuples, because in order to interpret the wall, we need to know how to interpret it, under what context, under what snapshot we need to interpret that log record. How to What is the schema of the table being changed when that wall was written, and all that information is there in the catalog tuples that were generated, that were present at that time. And since we need to preserve those catalog tuples in MVCC, we have to also keep track of what is the oldest transaction um, that that created these tuples, and thus it holds back the main transaction ID as well. And we will revisit this holding back resources a bit. Let's dive more into the actual mechanism of how the replication slot pres- main how the replication slot holds the LSN, holds the wall back, and what is its impact. So in this diagram, you will see that on the left side, we are maintaining snapshot of the transactions that are currently going. In the middle, you will see the wall stream. And for each wall, you will see the snapshot at that time on the left. And on the right, we see the progress of replication slot, how it is moving a lesson forward. So let's say assume that it starts with the first orange record, which is the first wall record of orange transaction. And let's assume that this is the first wall record in the wall stream. So it sends it downstream. It sends the next record as well. It sends the third record, which is the start of blue transaction. And it knows that a new transaction has started. It records it in the snapshot. It sends it downstream. The fourth record is sent downstream. If anywhere in between, while these four records are being sent, if the downstream tells that, okay, I have received fourth record, um, it will note it down as confirm flush LSN, but it won't change a lot, because let's say at this point, if the wall sender stops or crashes, or wall receiver stops or crashes, the wall sender has to start from the beginning of the orange transaction, because we have not sent the commit record yet for the orange transaction, and only the committed transactions really matter. So it has to go back, start from the orange transaction, and then proceed ahead. So it will still keep its restart LSN, which is the LSN from where a wall sender starts reading again, uh, pointing to the first wall record of the orange transaction. Okay, let's move ahead. The next record is the start of yellow transaction. It noted it down. The next is second record from wall transaction, still noted down, nothing changes. Now we see the first commit record, which corresponds to the commit of blue transaction. And let's assume that the downstream sent a confirmation that it has received and applied the commit record of blue transaction. So one transaction was committed and it need not be sent again. But still, if you note, orange is still the transaction which has the oldest LSN. And so if wall senders restarts at this point, it has to go back all the way to the start of orange transaction and start sending the changes. And so restarts LSN does not move even if the confirm flush LSN has moved ahead. Um, Now, what happens to the blue transaction? Even if we restart at this point, the blue transaction is not sensed because we know that the last LSN of blue transaction has been confirmed. Okay, so let's proceed. Something interesting is going to happen here. The orange transaction has committed now, and we send the commit record for orange transaction to downstream. Downstream acknowledges it. Now we know that at this point, orange has been committed, blue has been committed, and it's only the yellow transaction which is active. And so we can move the restart LSN to the start of yellow transaction. As you will see that the restart LSN 3 is now pointing to the yellow transaction. So that's how the LSN can be moved. And any wall records which are before the first wall record of yellow transaction can be released. They are not needed anymore and they can be removed from the disk. Sorry. Now, let's proceed a bit and we come to the first transaction of the green record. We record it in the snapshot. Now there are two active transactions. Then we see commit of yellow. So now there is only one active transaction. Restart LSN can be moved even further to the first record of the green transaction. When the green transaction commits, there are no transactions active. And when the next transaction pops up, which is the blue transaction, the restart LSN points to the first record of the blue transaction. This is how the LSNs in the replication slot move. And by tracking this movement, the upstream can decide which of the wall records can be freed, which of the catalog tuples are not needed anymore, and does also move the transaction ID, minimum transaction ID. Okay, what we saw was the regular replication, what happens at runtime. But what about creating the initial snapshot of the database or creating the initial logical view in order to set up replica? For that, we need to create replication slot. And when we create that, we will look at the arrow with label create replication slot. That's the wall record when the replication slot has started getting created. And at that point, there were two transactions active, yellow, orange, and blue. So the replication slot creation waits for these two transactions to finish. So till the eighth record, it has to wait. At that point, it again looks at what were the active transaction at that point, and you will see that the yellow transaction is only active. So it records the starting LSN of the yellow transaction. That becomes the first restart LSN of the replication slot that is getting created. And then the end of the orange transaction or the start of the green transaction becomes the confirm flash LSN and gives the first snapshot for that replication slot. If we run copy command at this point in the database, in the origin database, then we get the data that will that will help us set up the replica. That's exactly the data that we want for replica to be set up, and then start receiving the logical changes from upstream and start applying on the replica to move it forward. Okay. Now, logical replication is, as you might have noticed, it's a very versatile feature. It's very useful feature, and we will touch upon its use cases. How versatile is that at the end? But it's it's a risky feature as well because it requires to hold back so many resources, and thus it needs monitoring. We need to take care of not breaking replication and fixing the replication as soon as we notice that it has broken. There are two ways in which replication can break, logical replication can break. The first is that the wall receiver gets into an error. It encounters a situation from which it cannot proceed. For example, it received a logical change which says that table 1 was changed, but there is no table 1 on replica. Then wall receiver does not know how to proceed further, and it will quit. The launcher will notice it, and it will restart the wall receiver. While this is happening, wall sender will also notice that wall receiver has gone away, and it will quit itself. Once the wall receiver comes up, connects to the origin, wall sender will start as well. That's how, if you follow the arrows in this diagram on the left, then you will notice the flow that I just described. Now, while launcher is waiting for retry interval to pass, if DBA or somebody notices why wall receiver quit, which it logs in the server error log, and they go and fix that problem, for example, here creating the table that was missing, then the next time wall receiver will come up, it can proceed ahead. It will pass that point where the error occurred. If not, then it will again encounter the same error, quit, letting launcher know, wall sender will notice, and the whole system will restart again. And this error loop will continue as long as the error is not fixed. If it's a temporary error like a network glitch, the system will recover from it. But if it's something that requires human intervention, then somebody needs to go and fix the problem. What might happen, and we do that, we find out what the actual problem is by looking at the server error logs, or if we have set some error, some querying around server error log as it is available in Azure, there can be automated tools which can be used to detect this error and then fix it. However, sometimes what happens is wall sender takes longer to notice that the wall receiver has gone. In which case, if wall receiver comes up in before the earlier wall sender has quit, we may encounter busy replication slot error. And it can repeat again and again, thus shrouding the server error log and misleading us into thinking that the actual error is the busy replication slot. But in this case, what we have to do is we have to continue to look back in the error log and find out the original error. Sometimes busy replication slot is the real error if multiple replicas are trying to use the same replication slot. Usually there will be one replication slot per replica. In case multiple replicas are using same replication slot, then they can encounter this error, and in such situation, you may want to create separate replication slots for this replica. The origin side loop looks slightly different, where the wall sender encounters error, quits itself, wall receiver senses it, quits itself, wall launcher then senses it, waits for the interval, and then restarts wall receiver, which in turn connects to the origin, which starts the wall sender, and the replication resumes. If the problem which wall sender encountered was temporary, then it will recover from it. If not, then human intervention will be required. Okay, with that, I would like to conclude with some concluding remarks about logical replication. Um, I want to emphasize that it's a very versatile feature. It can be used to replicate data across PostgreSQL versions, across multiple platforms where PostgreSQL is running. We can do selective replication in the sense that we can just choose to replicate only few tables, even within those tables, only few rows or few columns. So there is a lot of selection possible in what data we replicate. Not only that, this mechanism can be used for heterogeneous replication. We can use it to pull data from PostgreSQL into data lake, for example, or to some other DBMSs. And that that continues to work by just using the origin and the wall sender there, but building our own wall receiver and apply mechanism depending upon the um, target. However, there are some limitations to the logical replication. One is there is no built-in bidirectional replication in logical replication. There is no DDL replication, but both of these features are being worked on actively on hackers, and hopefully in few releases we will see these limitations also been removed. When using logical replication, we have to be careful. We have to monitor the progress of logical replication, monitor the replication slots, watch for broken replication, watch if the wall is building up because of long running transaction, if the disk space is getting full because of wall buildup, because of the catalog tuples that are retained. Because the minimum transaction ID is also retained, there is smaller but positive chance that transaction wraparound will be reached, which is a very risky and very serious condition in PostgreSQL. All of these together can stop the origin from working. They can bring down the origin. So we have to watch for that. And with that word of caution, I will conclude my presentation here and we'll open up for question and a. Thank you.